I don't think we did this problem. Let me look it up. See what exactly this problem is. So this is problem 17 in the book. So this is the one that says use Green's theorem to evaluate the line integral and the boundary of the region lying between the graph of y equals x and y equals the square root of x. So let's see what we do on this thing. So so this is problem 17 in the book. And again, just thinking about, we might think about how we would, let's do it using Green's theorem, but let's then look at what you would do to do it as a line integral, just for practice. So Green's theorem says that you take the integral over the region of the partial of n with respect to x minus partial of m with respect to y times dy dx. So first thing we have to do is take the partials, partial of m with respect to n with respect to x. So n is over here, so you get y plus minus the sine of x, sine of y. I think that's partial of n with respect to x. And then you do the partial of m with respect to y, which would be sine of x, sine of y. So then, do you agree with that? So we're going to agree with respect to y first. You draw one of these rectangles. So the upper boundary would be y equals the square root of x. The lower boundary would be y equals x. And x goes from 0 to 1. And so you'd have y minus sine x sine y. That's the partial of n with respect to x. Subtract the sine of x sine of y. Oh, that makes it easy because that falls out. I think they pick these integrals so that they do simplify considerably once you've done these two partial derivatives, because in this case the sine x sine y drops out, so you just end up with the integral from 0 to 1. That's not always the case. I guess the thing is, if you might end up not improving things as far as the level of difficulty. So then you would you'd integrate with respect to y first. So you get y squared over 2 evaluated between x and the square root of x dx. So you get square root of x squared, so that's x over 2 minus x squared over 2 all times dx. And then you integrate with respect to x. So you'd get x squared over 4 minus x cubed over 6. Don't need this integral sign. I just got to turn my little sound off here. And then evaluate that between 0 and 1. So you just end up with 1/4 minus 1/6, which is 1/12. 3/12 minus 2/12, 1/12 is the answer. So now the question is how this one actually may be difficult. We'll see what happens. Let's just see if we can figure out how we would do the line integral. So, and this is in differential form, so it gives us, practice at trying to do it in differential form again. You still have to come up with these parametric equations. So you've got two parts. You've got part 1, which would be from here to here. So I would say you let x equal t and y equal t, and t would go from 0 to 1. So that would be your first interval going here, and you have to go counterclockwise, so we have to do this one first. And the second part, I've seen, some cases where they start t over again. It's not like t has to be continuous, I don't think.
I mean, that makes sense to me because the integral, because you're really just making it two integrals either way, right?
Yeah, so in this case, it may be more convenient to just start with t equals 0 again. I think if you have a line, usually they do that when you have different line segments connected together. But if it's a more complicated function, I think you can start over again. So I'm going to do that. So I think all you do is say x equals t and y equals the square root of t. And again, t would go between 0 and 1. Actually, no, it wouldn't. That's not exact. It's got to be minus 1. I guess it's 1 minus t. Is that right? 1 minus t. And is it then that's the square root of 1 minus t? Hmm? Oh, we got some candy here.
Yeah. You can have a piece or two, can't you?
Yeah, I can do that.
That's butterscotch.
Oh, is it?
Yeah.
Is there an orange?
There's not an orange hard one. There might be an orange soft one left. Do you like orange?
Yeah.
Those should be orange.
Okay, great.
You want another one?
No, thank you.
Yeah, there's another one.
No, give me another one. What, are you trying to clear out here?
I'm sorry. I understand.
You're tempting me.
I know. I shouldn't do that, but is that enough? You sure?
Yeah. But the square root of 1 minus t
We
is
missing Mia
just 1
today?
minus square root of t.
Say it again.
Is Mia here today?
No, she's, what is she doing today?
I can't remember.
Yeah, some school thing.
All right.
Okay, anyway, you said what it should be?
Would it be 1 minus square root of t or that?
Oh, 1 minus the square root of t or the square. Let's see. Well, let's look at the boundary condition. Well, yeah, you're probably right. So you think it's 1 minus the square root of t. So let's just try that out. So t equals, we'll let t equals 0, a half, and 1. So x is going to be 1, a half, and 0. So that part works out right. It's this one. So if you put in y is going to be 1 minus the square root of t, which is going to be 1. And we'll do the other end. If you put in 0, you get, if you put in 1, you get 0. And if we put in a half, we'll get a quarter. So it's 1 minus a quarter, which is 3/4. So when x equals a half, 3/4. Yeah, I think you're right.
I'm not really sure, but I think the endpoints would they be the same?
Pardon me?
I'm just trying to figure out.
Yeah, what I'm thinking about is if you
Because I think the square root of 1 minus t would still give you the same.
it would give you the same stuff. I'm just the endpoints are okay. It was just I was picking this point in the middle so that if you because the square root of a half, did I do that right? 1 minus the square root of, well, I'm going to cheat and look at the solution manual. I can't think of this hard this morning because I'm not sure if that does work or not. Because this, you actually get 0.707, not 3/4. So let's see what they do here in the solution manual. 17 section.
Yeah, I think you might be right the first
Oh, I was right the first time. Yeah, let's see. Yeah, it works out for the endpoints, but I just picked one point in the middle. Oh, well, they're not going to do it because they're just using Green's theorem. Let's try the other one. Because this should be 0.707. It should be the square root of 2 over 2, right? 0.707. So if I do the square root of 1 minus t, and if I let t equal 1/2, I get the square root of 1 minus a half, which is 3/4. Square root of 3/4. That's the square root of 3 over 2. Square root of 3 over 2. So that doesn't seem to work either, right?
Well, thinking about it, I guess it has to be that because
Let me
y
close the door here.
y is the square root of x anyway.
So, what do you?
I guess it has to be that because y is the square root of x anyway. I forgot to think about that as far as the parameterization goes.
Can you write it down?
If x is, well, just looking up there, if x is 1 minus t,
Yeah.
then just y is the square root of that. So I guess it's got to be right.
Oh, okay. So you think that's right?
Yeah.
Okay. Okay. So for the first part, dx is equal to 1 and dy is equal to 1. Well, 1 dt. And here you'd have dx would be equal to negative dt, and dy would be equal to negative 1 over the square root of 1, actually 1/2. So it'd be negative 1 over 2 square root of 1 minus t. That would be dy in terms of, and then times dt. And then you would plug that in. Yeah, this is looking grim to us right now. So if you plugged in, let me copy this equation over. Whoops. Okay, so now we'll put this integral together. So you get the sine, and this is it from t equals 0 to 1 of the sine of x, which is t, times the cosine of y, which is t, times dx, which is dt. And then you have the second part, which is x, which is t, times y, which is t squared, plus cosine of t, sine of t, the whole thing times dt. So that would be the integral along the first path, the straight line. sine of t cosine of t dt. Okay, and then you'd have the second integral, which would be from 0 to 1 again, and you'd have the sine of 1 minus t times the cosine of the square root of 1 minus t times dx, which would be negative dt, plus x times y, which would be 1 minus t times the square root of 1 minus t multiplied by sine of x, which is t, cosine, sorry, cosine of t times the sine of y, which is the square root of 1 minus t, all times dt, which is negative 1 over the square root of 1 minus t times dt. So at least the square roots cancel out. I guess it's not impossible, because your first integral, you'd end up with 2 sine t cosine t, because you combine these two together, plus t squared dt, integrated from t equals 0 to 1. And then you'd have the second integral, which would be the integral from 0 to 1 of I think you end up with this. Do these cancel out? It's because you got sine of 1 minus t cosine squared of 1 minus t. No, they're switched. Yeah, that would be hard. To do this integral, because you've got different arguments in the sine and cosine. So I'm not even sure how you do that. If you wanted to, normally you have to have these have the same argument to be able to use substitution. I think we can say it's hard. We're not going to do it. Did I assign homework from this section yet or not?
13.4.
Yeah.
No.
Okay. I just wanted to see which ones I included. So I put 12 in there. Just want to redo that one. Now so the ones I only have 3 problems assigned here. The next one is calculating the work done on a particle that is moved counterclockwise around a closed circuit path C, and I don't think I've worked a problem like that. I don't think I have one in the in my notes. So let's work on one of those. It's really so the way the problem works is you have some force vector field which is not conservative, because these are all non-conservative things. Because if it was conservative, we'd have the integral would be 0. So this is the force field vector, and the curve is x squared plus y squared equals 4. So that's a circle of radius 2. So it's going to look like that. And so we're going to move counterclockwise. And so because it's a circle, we would use the parameterization x equals 2 cosine t and y equals 2 sine t. And t would go between 0 and 2 pi. If we were to if we were going to use the line integral. But what we're doing here is we're using Green's theorem, so we don't, this one we could actually probably do the line integral. Might not be as daunting. So in this case, if you draw a vertical rectangle like that, I'm just thinking about this because this, if you normally the integral, it's this double integral, and we got the partial of n with respect to x minus the partial of m with respect to y times dA. And the lower limit, you'd have to put this into the Green's theorem is, you could do this as a rectangular coordinate system, or you could do it as a polar coordinate system. I mean, you could rewrite these and do this area, find this area using polar coordinates. What you'd have to do is take the partial derivatives and then use these substitutions. They wouldn't be parametric substitutions, but they would be polar coordinate substitutions. So there's two ways I think we could set up this problem. So let's write them both out and see what we would do. Make sure we agree with this. So you take the partial of this partial of n with respect to x, that would be y, and then you subtract the partial of m with respect to y, which would be x. No, that's not true. Partial of n with respect to x is 1. So the partial of this with respect to x is just 1. And then you subtract the partial of m with respect to y, which would be x. And then you multiply by dy dx. And you'd integrate from negative the square root of 4 minus x squared to positive the square root of 4 minus x squared, and x would go from negative 2 to positive 2. So I think that's how you would set up the integral in rectangular coordinates. In terms of polar coordinates, what you would do is you would integrate from r equals 0 to r equals 2, and you'd integrate from theta equals 0 to theta equals 2 pi, and you would replace x with 2 cosine theta, and you'd replace dy dx with r dr d theta. Let's see what the book says. They do. This is problem 21 in the book. So they convert it to polar coordinates. So they choose the second option. So you would first integrate with respect to r. So this 1 minus 2 cosine theta is just a constant. If you integrate r dr, you get r squared over 2. We evaluate that between r equals 0 and r equals 2. We've got the integral from theta equals 0 to theta equals 2 pi, and we got a d theta on the end here. So if you plug 2 in there, you'll get 4 over 2. So you get 2 times 1 minus the integral 1 minus 2 cosine theta d theta, and the integral of 1 d theta is theta. The integral of the cosine is the sine. Evaluate that between 0 and 2 pi. And what happens is the second term drops out because the sine of 0 is 0 and the sine of 2 pi is 0. So you just get 2 times 2 pi. The lower limit would be 0 and the upper and lower limit here would be 0. So you end up with 4 pi as your answer, which is the right answer. Now, doing it in Cartesian coordinates wouldn't be too bad. You'd integrate with respect to y, so you'd get 1 minus x times y. Then you plug y in. So you'd have, let's just do that for the heck of it. Let's see if we can do the Cartesian coordinate solution here. So you'd integrate with respect to y. You'd have 1 minus x times y, evaluating between negative the square root of 4 minus x squared and plus the square root of 4 minus x squared dx. So when you plug in the upper limit, you get the square root of 4 minus x squared, and you subtract the lower limit, which is negative the square root of 4 minus x squared, multiplied by dx. And so you get 2 of those. So you'll have 2 times the square root of 4 minus x squared minus x times the square root of 4 minus x squared. The whole thing times dx. So the integral of this one is not going to be that hard because you're going to have, you'd let u equal 4 minus x squared, so du would be equal to negative 2x dx. Now here, what do you think we do? Yeah, trig substitution. Or you look it up in a trig table. Trig substitution. So that sounds like a good thing for you guys to do. Why don't you do that? Why don't you solve that? Solve that equation. The answer is 4 pi. I'll do it after class as well. I'm not trying to get out of doing it. I just figured it'd be good something to do outside of class. Just kind of a review of stuff we've done. Gives us some appreciation for polar coordinates. Okay. So that's calculating work. The last thing that they use is using it to find areas, which is it's interesting. I don't really think it's that useful because you can use other techniques to find areas. So, but we'll look at one. We'll look at one example here. So the theorem for a line integral for area is if R is a plane region bounded by a piecewise smooth simple curve C oriented counterclockwise, then the area of the region is given by the line integral of 1/2 times x times dy minus y times dx. But so in this case you actually do the line integral, so you don't have to do the double integral. Use the equations for curves defining the area to rewrite the terms of x and y only. The limits will be x or y only. Yeah, because it's just a single integral. So you got this integral, which is a line integral. I was just thinking about it, because what we would have done in the past would have been to parameterize these but they're saying to use the equations for the curves defining the area to rewrite the terms for x and y only, or x or y only, and the limits will be, so let's see what that means, because I've forgotten. Oh, so yeah, I did it both ways. So let's look at both ways. So this the curve. So the curves are y equals 3/2 x, and the curve y equals, there's three curves, so it's like a triangle. So let's draw what this looks like. We get a piece of graph paper. So we got three lines that are defining the area. So we've got the first line, which has a slope of 3/2 starting at the origin. So we go over 2, up 3. So it's right like that. And then we go, so that's from x equals 0 to 2. Then we have the line negative x over 2 plus 4. So we go to plus 4, and we have a slope of negative 1/2, which looks like that. And then we have x equals 0, so it must be this, it's this area right here. So we're talking about this area, which we can do. You know, you could, it's a triangle, so we could do it just using, but this is just to show that it actually works. So the first, going counterclockwise, this would be the first line, this would be the second line, this would be the third line. First I thought it went like this, but then I got to this last one. So what it's saying is you take the derivative of y to get dy, and the same thing down here. And here we take the derivative with respect to x dx, because this is x equals something instead of y equals something. So I guess, you know, here you could write the equations as y is a function of x or x is a function of y. You just have to reflect the appropriate variable you choose. So what you end up with is these three integrals. So you've got x times dy, which is 3/2 dx, minus y, which is 3/2 x, times, what did I do there? X times dy minus y times dx. Okay, yeah, so that's right. And then the next one, you take x times dy, dy is negative 1/2 dx, minus y, which is defined by the curve, times dx. And then the final one, and here you're integrating from x equals 0 to x equals 2, and here from x equals 2 to x equals 0. And then this last one, you got x times dy. Well, x is 0 times y times dx. dx is 0, so you get 0 for the third integral. X times dy minus y times dx. And actually I show going from x equals 0 to x equals 0, but I think it actually would go from y equals 1 to y equals 0, but it's still 0 because every term is 0. So now you got this in terms of x, so you can simplify it, integrate it. So let's go to the next page. So all of this stuff put together from the previous step apparently is, yeah, what happened? Did some of this stuff cancel out here? Yeah, this first one goes to 0 because you've got x times 3/2 times x, and x times, so this one goes to 0 because these cancel out. The third one went to 0 because these two terms are 0. So the only thing that was left was the center equation. So we simplify that, we multiply it out, so we get that, and these cancel out. So when you multiply it, the only thing that's left is negative 4 dx. So you integrate, well, negative 4 divided by 2 is negative 2. Integrate dx, you get x. You integrate from 2 to 0, so you have 0 minus 2, plugging it in here. You had a negative 2 out there, and so you get the area is 4. So that's how you do it without having to parameterize the equation. But if you did want to use the technique that we've used in the past, you would take each one of those curves and you would parameterize them. So for the first curve, you let x equal t, you let y equal 3/2 t. So dx is dt and dy is 3/2 dt. Okay, so that's the first curve. So we have substitutions for x and y and for dx and dy. So this is, using we're going to use the differential form of the equation to make it into a parameterized integral. Then we have the second curve, which is the one with half a slope. And again, you can figure out what it is by doing what we've done before. You've got the beginning point and you've got the end point, and you've decided what t is going to be. What you need to figure out is what a and b and c and d are based on those restrictions. So start point, end point, start t, final t. You can figure out what a, b, c, and d are under those restrictions, and you can come up with the parameterized equations for the second straight line. If you do that, I'll just give you the equations if you want. I'm sure you can solve these. So you get x is 6 minus 2t and y equals t plus 1. So that's the parameterization for the second part. And then the third part, and then you take derivatives because you need those to do it from the differential form of the line integral. And then you've got the last one, which is x equals 0. And we're just continuing on with starting with t equals 3 to t equals 7. And these are the 2 points. So t equals 3, x equals 0, y equals 4. T equals 7, x equals 0, y equals 0. And you plug those in to find a, b, and c and d. Turns out there's only one equation. One is x equals 0 and y equals 7 minus t. So I didn't write that down, but x equals 0 is the other one. So you get dx is 0, you get dy is negative dt. So those are so we got everything. So then you plug them into you get 3 integrals. So here are the 3 integrals. So you've got x times dy minus y times dx. You get the second integral, x times dy minus y times dx. And the final one. So this one goes to 0. This one cancels out. So you end up with just the middle term again. And if you do that, so you're only integrating from 2 to 3, and you get 8 times dt. And if you integrate 8 dt, you get 8t evaluated between 3 and 2. So you get 24 minus 16, which is 8. 8 divided by 2 is 4. So you get the same answer. So that's kind of how that one works. If you want to find the area. Obviously, it's a lot more work than just using the equation for a triangle, but if you have a more complicated situation, then. So there's the homework. Not too many. I might give you an extra couple here. So let's see. So 12. Let's do 20 as well. 22. That's a work one. And let's do 27 as well. That's an area problem. So basically what we've shown is if you have a complicated line integral, you can sometimes use Green's theorem. It has to be a line integral that's a closed curve, closed simple curve. but you can find the line integral around a closed curve using Green's theorem. Sometimes you can you can rewrite a double integral as a line integral. Sometimes one's easier than the other. So, and then you can find the Green's theorem has applicability to force to work around a closed path. We also know that Green's theorem basically says that the work or the line integral around a closed curve in a conservative vector field is 0 because the partial of n with respect to x is equal to the partial of m with respect to y. And you can also use it to find areas by using that theorem. Okay, so we're moving on. We've got 4 sections. Is it 4 sections or 3 sections? So we're on section 6 now, right? 6, 7, and 8. Is there a 9, 10? Oh no, wait, here we go. Chapter 15. So we just finished 4. So we got 3 sections left. We got 3 weeks. So I think we'll make it. Just barely. Okay, so the next thing we have to talk about is parametric surfaces. So we talked about parametric curves, and we needed those to be able to calculate line integrals in both scalar fields and vector fields. So what we're doing now is we're going to do surface integrals in scalar fields and vector fields. So we need to be able to define a surface in a parametric fashion. We've done it in functional form. Z is a function of x and y, and or z is a function of r and theta, and yeah, or you've got the spherical coordinate system. So we have those different coordinate systems. We never dealt with surfaces in a parametric form. So let's look at that. So the big thing here is your parametric surfaces have 2 parameters. So you have the x coordinate, and you define the parametric surface by, you can define it, I guess you can define it as x, y, and z, the coordinates, the set of coordinates x, y, and z that satisfy this parametric equation, or you can set it up as a position vector in 3-dimensional space. And just like with curves, parametric curves, there you define an interval of t. T is from 0 to 2. T is from whatever, 2 values of t. When it comes to parametric surfaces, you have a domain of u and v. So you have, it's almost like in the uv coordinate system, you define a region in the coordinate system. For a line, you're defining t along a number line or a one-dimensional thing. So it's because you have this vector which is defining a surface in xyz, in the xyz whatever you want to call that, domain. It's not really domain. What the heck would you call it? The xyz coordinate system, but then you're actually defining u and v in a separate uv plane. So it says let's plot some. So that means I'm supposed to open up my graphing program, because you can do that with this program. So if you go to 3 dimensions, and you can put in the equations parametrically. So you can see there's u and t. So I'm just going to pick some out of here that's in the book. So you have x is 3 cosine of u, and this is 3 sine of u, and z is equal to v, and we're going to go from 0 to 2 pi. Actually, they use t and u, sorry, not u and v. So let me go back, change this to t. T and U. So this is U. And I'm just taking the first problem example in the book. So it goes from 0 to 2 pi, and V goes from 0 to 4. U goes from 0 to 4. Let's see what it looks like. So there you go. It's a so this is a cylinder in 3 dimensions. Okay, so that's one example. I just need to get it. How do I quit this thing? Close that. Yeah, okay. 3 dimensions. The 3-dimensional one here. Okay, so parametric equations. Here's another one. Sine of t cosine of u for x. Sine of t sine of u for y. And the cosine of t for y. Sine t, cosine u, sine, and we want to go from u equals 0 to pi, or this t goes from 3.14159, and u goes from 0 to 2 pi, 6.28318. So that's the equation for a sphere in this parametric format. One more. Well, that's not. Yeah, okay, we'll do one more. So x is t. Oh, okay. Just going to say the cosine of u, and this is the sine of u. T goes from just 2 values, doesn't really matter. I'll say 5. And this goes to 2 pi, 6.28 something. Oh, that's not what I expected. I must have done something wrong. Let me try this. Let's just put t in there. T. Yeah, okay. It's a cone. That's what it was supposed to be. So that's a cone using parametric equations. Okay. So here's some examples of things that we've seen in the past. Because we've looked at all these shapes, cylinders, spheres, cones, probably ellipsoids, paraboloids, all these kinds of things. And so they have these shapes. So, for example, a plane, the plane in this case this would be aligned with the x-axis, I think. So it's the plane z equals y. And so there, it's x equals u, y equals v, z equals v. And so the vector that defines that surface in terms of the u and v. And, you know, the bigger u and v is, it probably goes from negative infinity to positive infinity, because that plane goes out in all directions. So here's another one. It's a little more complicated. What you do is, so if you solve for z, you get z is equal to 6 minus x minus y. And the corresponding parametric equation is x equals u, y equals v, and z equals 6 minus u minus v. So apparently the pattern here is that you let u, for planes, you just let x equal u, y equal v, and z is replacing x and y with u and v from your previous definition. So that seems pretty simple in terms of coming up with parametric equations for planes. So what we'll do next time is we will look at some more of these standard shapes and look at how you can relate the Cartesian equation into a parametric equation, because ultimately you're going to need they'll need to be in parametric form to be able to do the surface integrals. So we'll save that. Stop my recording.